welcome to OMSI's virtual Science Pub. My name is Jenny Crane, and I'm an educator at OMSI, and I'm going to be your host tonight. Before we get started, I have a couple things to tell you about what's going on at OMSI these days. First and most importantly, OMSI is open. We're so excited about our current exhibit, Dinosaurs Revealed. It will be open through September. There's 26 animatronic dinosaurs, dozens of fossils, plus 2 life-size dinosaur skeletons. Advanced tickets are highly recommended as we are sold out for the coming weeks. You can also catch a show at the planetarium or the Empirical Theater or take a tour of the submarine. Check out our website for the most up-to-date information and to view our COVID safety guidelines. I hope you enjoyed tonight's pre-pub trivia and music by local Portland artists Wild and Red, a collaboration of 2 bands, Red Bird and Shelley Rudolph and Tim Gilson. Putting on these live shows takes a lot of work, and we have an amazing partner that helps us with each of these Science Pub events. A big thanks and a shout out to Celestream for providing the live streaming services for tonight's Science Pub. We really appreciate their support. Coming up, we have our 9th virtual OMSI After Dark. This is a best of event. We have found so many delicious products from Oregon that we wanted to celebrate with an event honoring the best beers, ciders, seltzers, and snacks from the past 7 virtual OMSI After Dark. Tickets include 10 items and access to the virtual event. You can find more information at omsi.edu/afterdark. We're also hosting virtual workshops. You can learn to make cow's milk fresh mozzarella or a personalized batch of kraut and kombucha. Visit omsi.edu/workshops for more information. Help us put the pub back in Science Pub. We encourage you to order tasty food and beverages from one of our regional partners. So if you haven't been to a virtual Science Pub event before, here's what you can expect. We'll have 15 minutes of trivia to warm up. This is going to be Volcanoes themed trivia for today. You can get a pen and paper and follow along at home and see how you do compared to our OMSI educator we're going to put to the test. And after that, we'll have a lecture by Gina Roberti, who is a science education coordinator at the Mount St. Helens Institute. After the lecture, we'll have some time for question and answer. You're welcome to put your questions in the Facebook Live chat or in the YouTube Live, and we'll be keeping track of them and then circle back to them at the end and have Gina answer some of your questions. If you enjoyed tonight's lecture, please consider making a donation or purchasing a Science Pub pint glass. But more than anything, we're just happy you're here. There's no pressure to donate. Our mission at OMSI is to inspire curiosity by creating engaging science learning experiences for people of all ages and backgrounds. So sit back, relax, and enjoy a great lecture right after our trivia. So this week we have Jen Powers from OMSI who's going to join us in some trivia. Grab a pen and paper and you can play along at home. Hey Jen, it's great to see you.
Hey Jenny, nice to see you too.
What are you most excited to learn about volcanoes tonight?
Pretty much anything. And really what I'm most excited about is that Gina is a education coordinator. And so that really speaks to my heart as a science educator as well. I'm really excited to see all her videos and her talk.
That's awesome. So let's get started with our trivia game. There's 10 questions. I'll read it out loud and give you time to guess and then reveal the answer before moving on to the next one. You ready?
All right. Yes, I'm ready.
All right. So according to the U.S. Geological Survey, what defines an active volcano? A, any volcano that has erupted since the last ice age, 10,000 years ago. B, any volcano that has erupted at least one time every 5,000 years. C, any volcano that has erupted in recorded human history. Or D, any volcano that has erupted since the time of the dinosaurs, 165 million years ago.
Wow. Those could all be realistic answers, but I'm going to go with B.
Let's see. It was okay. So there are approximately 145 active volcanoes in the U.S., including Hawaii, and that tracking whether a volcano is active based on whether it has erupted in a human time period is incorrect, as the dormant intervals between major eruptions at a single volcano may last hundreds to 10,000 of years. I guess that goes back to that whole long geologic history, doesn't it?
Yeah.
All right. Let's try another one. What part of the world has the most active volcanoes? A, the Ring of Fire, which is the volcanoes around the Pacific Ocean. B, the ocean floor. C, the Yellowstone hotspot. Or D, the Hawaiian hotspot.
Wow. Has the most active volcanoes. I will guess A, because that's where we're at.
That was my guess too.
No, that means it's wrong.
Then I was like, oh, that was so tricky. I should have guessed this other one that was actually.
I don't know. I'm going to go with the one that I was not going to. Yeah, that was the one that I was absolutely not going to guess. The ocean.
The ocean floor, yeah. So, of course, all those volcanoes that we don't get to see that are at the floating ridges. Okay.
That's amazing.
I know, it is kind of amazing. So much, and especially because, most of these weren't discovered until this last century.
Yeah.
Okay. Which of the volcanoes in the Cascades has been most active in the past 4,000 years? Mount Shasta, Mount St. Helens, Glacier Peak, and Mount Rainier.
I'm going to go with Mount St. Helens. Seems like the logical answer.
I think that's a great answer.
Yeah.
For once, it was one that was not trying to be too tricky, yes.
Yeah.
Of the 13 potentially active volcanoes in the Cascades, 11 have erupted in the past 4,000 years, and more than 100 eruptions, most of which are explosive, have occurred during this time.
Yeah, that's pretty amazing.
Yeah. All right, number 4. How long did it take ash from the 1980 eruption to travel around the globe? 2 days, 2 weeks, 2 months, or 2 years?
I want it to be 2 days, so I'm going with A.
Cool.
Nah.
2 weeks.
Go with my second guess for all of these.
It does say 2 days later, some came to the northeastern United States. So we're already
pretty fast.
Later. We've made good progress here.
Well, that's pretty impressive still, 2 weeks.
Yeah, absolutely. All right, number 5. Why can certain types of rocks formed in volcanic eruptions float? A, the rocks are made of particularly lightweight minerals. B, the rocks are made up of styrofoam. Probably that. C, the rocks contain many air pockets from trapped gases. Or D, the rocks have the Wingardium Leviosa spell cast on them.
As much as I love D because I'm a huge Harry Potter nerd, I'm going to go with C, the trapped gases.
Yes, the trapped gases. So pumice is a rock formed in explosive volcanic eruption. We actually found some pumice this weekend. My family and I were up on the Toutle River by mountain.
Oh, that's awesome. Yeah, they're really, really light.
Yeah.
Yeah.
Okay. 6. Which volcanic hazard threatens the most number of people living in the Cascades? Is it A, ashfall, B, lava flows, C, pyroclastic flows, or D, debris flows, also known as lahars?
Wow, that's a great question. I'm not going to go with lava. Pyroclastic flows is definitely what took out Pompeii. I don't know if any of us are living close enough, though. So I'd go with ash.
Yeah, or think about all the glaciers and rivers coming off of our Cascade Mountains and what would happen, when big explosion occurs to kind of liquefy all that stuff.
There, we can also go with D.
You could.
The lahar flow.
That's a legitimate guess. Probably right. Yeah, so lahars or debris flows are a mixture of mud and rock that look and behave like flowing concrete. So they do not have to be triggered by an eruption, but they can often follow an eruption.
Sounds dangerous.
Yeah, I would not want to be right in the lahars. So where does the United States rank globally for its number of active volcanoes? Do we have first place, the most, second place, third place, or 14th place? Big jump there.
Third.
All right, let's see. Third, yeah.
Nice.
Third behind Indonesia and Japan, which when you think about it is kind of crazy. Japan and Indonesia are both geographically.
Very small island nations. So they are, I guess, active volcanoes are pretty prevalent.
Yeah. Okay, number 8. How often, on average, have volcanoes in the Cascades erupted in the past 4,000 years? Is it A, 1 to 2 eruptions every 50 years, B, 1 to 2 eruptions every 100 years, C, 1 to 2 eruptions every 500 years, or D, 1 to 2 eruptions every 1,000 years?
Going with B, maybe?
Okay, let's find out. Hey, you're right.
Nice.
Yeah, 1 to 2 eruptions every 100 years. And it's been what, 40 since the last one?
Yeah. We're due for another one here.
Yeah, I know it doesn't exactly work that way, but I'd like to think that maybe I get to see him.
Yeah.
Okay, 9. Which of the following is the best analogy to describe the shape of the new glacier that has grown since the 1980 eruption of Mount St. Helens? Is it A, shaped like a lollipop, B, shaped like a loaf of banana bread, C, shaped like a donut, or D, shaped like Laffy Taffy?
Wow. Does Laffy Taffy have a specific shape?
That is a good question.
Well, I was up on the top of Mount St. Helens not that long ago, so I should know. But C, because a donut sounds really good.
Yeah, of all of them, that's the one I'd probably most like to eat.
Yeah.
And it's also the one that's
Perfect.
You climbed to the top?
Yeah, it was great. Yeah. Well, except for that last little part that was all ash. That wasn't quite as fun.
Yeah.
The rest of it was great.
And then last but not least, if you're following along at home, you can kind of tally up and see how you've done. Some of the most recent scientific studies at Mount St. Helens investigate why Mount St. Helens is further east than other volcanoes in the Cascades Range, such as Mount Rainier and Mount Hood. What evidence helps scientists answer this question? Are they looking at evidence of layers of rock and ash, which tell of past eruptions? B, evidence from seismic imaging, which tells the structure of the Earth beneath the surface? C, evidence from paleomagnetic data, which tells the orientation of minerals when they formed? Or D, evidence from other volcanic ranges in South America?
Wish there was an all of the above answer because they all sound like cool things to study.
Yeah.
I mean, I guess volcanoes are kind of openings in the earth, right? And so I would be most interested in learning about the seismic imaging and what's happening underneath and why the volcano has erupted in that particular spot.
That seems entirely plausible to me. And it is true. Yeah. So evidence from seismic imaging, which tells the structure of the Earth beneath the surface. Well, yeah. I look forward to hearing a little bit more about that.
Yeah, me too. That's really interesting.
Well, thank you so much, Jen, for joining us. So next, we are going to have our speaker, Gina Roberti. She is a geologist, naturalist, and educator who grew up digging quahogs and exploring the shorelines of Narragansett Bay in Rhode Island, which is also the state with the largest coastline per capita. Since graduating from Brown University with a degree in geology biology, Gina spent several years working as a geoscience educator in various geologic regions in the western U.S., including the Colorado Plateau, Snake River Plain, Klamath-Siskiyou, North Cascades, and presently the active Cascade Volcanic Range. In each of these places, she taught thousands of youth and adults about earth science in a variety of field-based and classroom settings. Gina currently works with the Mount St. Helens Institute. She strongly believes in the power of education to inspire awareness, appreciation, and stewardship for the natural world. When Gina is not working, she can be found on long walks or cross-country skis, often in the company of birds. Thanks for joining us, Gina.
Thank you so much for the introduction. Hi, everyone, and thanks for joining us this evening. My name is Gina. I'm really excited to be presenting tonight for OMSI. It's quite a privilege. And I'm here to share my perspective of Mount St. Helens and other volcanoes in the Pacific Northwest. Mount St. Helens, the crater glacier is pictured behind me, and the rim is the flat rim in the back there. And I'm going to be speaking about my perspective, which is a perspective informed by my training in Western science. So I studied geology in college, and I currently work as a science educator. And I want to recognize and state that science is just one way of knowing the world. It's one lens through which we understand the natural world and the landscape around us. And I'm here tonight to speak about that one lens without excluding the many other ways of knowing, including traditional ecological ways of knowing. So I want to honor the fact that there are many ways of understanding the volcanoes and landforms that we have here in the Pacific Northwest. And I'm here to give you all some perspective from the science mind so that you have a new appreciation and a new lens for looking at the volcanoes here. So without further ado, I'm going to share my screen and begin this presentation. We'll begin with this photograph, looking down on some of the familiar volcanoes to us in Portland here, Mount Hood in the foreground, and then some of, I like to say, the extended family of volcanoes in the Cascades Range. Many of you may be familiar, Mount St. Helens over to the east with the flat top, Mount Adams Mount St. Helens to the west with the flat top, Mount Adams, the snow cone shaped mountain further to the east, and then Mount Rainier directly almost center in the background. And I currently work as the Science Education Coordinator at the Mount St. Helens Institute. It is a nonprofit that works to connect people with Mount St. Helens and volcanic landscapes. So much of what I'll be speaking about today is through the example and lens of Mount St. Helens and what happened in the eruption there in 1980 and subsequent eruptions. And I'm happy to answer questions about the Institute and how to connect with the volcano at the end of this presentation. We're going to begin with a map here of North America, where we all presently call home. And this map is a map created by a project out of California. And what this map does is it's an interactive map. And on this map, one can superimpose many different colors. And on this map here, all of these different colors represent the territories of people, communities of people that have called this place home and their traditional cultural lands since time immemorial. That means since before time of human memory. So people have been in relationship with the land and its landforms. We can flip over from looking at where different colors represent different territories, geographic of people, to where different languages were spoken. And this map toggles here. You can see the names of some of these languages. And if we zoom in on the Pacific Northwest, we see we're zooming in on an area here where we have a very high density of many different types of colors overlapping, meaning many individual, distinct indigenous communities have called this place home since time immemorial. If we zoom in, for example, to the location of one of our Cascades volcanoes, Mount St. Helens, we see there is still an overlap even where the location of Mount St. Helens is, which is somewhat near where the white label is that says Cowlitz. And we see some of the languages of people that call this place home include Cowlitz, Klickitat, Yakima, and Nisqually. And in fact, some indigenous names for the volcano Mount St. Helens reflect the fact that Mount St. Helens is an active volcano. And the Cowlitz name, La-Wet-La-Kla, actually is comprised of two parts. The La-Wet-La part means the smoker, and then the Kla at the end is a personifier, so person or being who smokes. These names reflect the fact that Mount St. Helens has been the most active volcano in the Cascades Range in the last 4,000 years, as we learned during trivia, and reflect the fact that this landscape is constantly one of change. Today, the 29 federally recognized tribal nations in Washington are located on much smaller reservations than the land these people once occupied. So the reservation lands are in yellow on this map, as compared to the entire state of Washington, which was covered in color on our other map. And so today, as we think about the landforms and the landscape, I do want to recognize the fact that these communities of people were severely disrupted by the movement and moving in of European and Western settlers. This included disruptions such as disease, warfare, and loss of land, which led to dispossession of land. So we're speaking about a landscape and we're speaking about landforms, which are culturally important to many people, and also many people who did not have the opportunity to live full lives because communities were wiped out because of disease with this change. It is a privilege for us to be able to frolic and play and maybe visit the crater of Mount St. Helens or the summit of Mount St. Helens in the wake of such a history of dispossession. So we're going to begin here by playing a video, and this video is going to give some context for this talk and what we're focusing on. I really love this video. You may have seen it. And as I play this video, I want you to think about the following questions. What information is familiar to you? What information is unfamiliar? And what information makes you curious? This video was produced by Oregon Public Broadcasting in partnership with the Washington State Department of Natural Resources. And Melanie will provide a link to this video at some point during this presentation. So Jason, if you're willing to take it away and play this video, that would be stellar.
At 8:32 in the morning, not very long ago, one of the most powerful forces in nature woke up in Portland's backyard. But Mount St. Helens isn't the only active volcano in the Northwest. We're surrounded by them. So what's up? Are we going to wake up some morning to a new Mount St. Helens?
Right now, we recognize about 25, 26 places in Washington and Oregon where magma has come out of the ground in the last 10, 12,000 years.
Seth Morin leads the U.S. Geological Survey's Cascade Volcano Observatory. With his team and partners around the region, he keeps tabs on the volcanoes in the Cascade Range. These are the folks who can help us understand if any of these volcanoes might blow like Mount St. Helens did. Many of the volcanoes last erupted thousands of years ago, which might make it seem like they're dead. But
a volcano that's active is a couple 100,000 years old and has erupted at least in the last 10, 15,000 years.
1,000 years seems like a long time to humans. But if a volcano lived for just one day, those 1,000 years would be more like just a few minutes. In other words, these volcanoes aren't done.
There's reasons to believe that it could happen again.
Whether they wake up tomorrow or 1,000 years from now, Seth says around 8 pose the greatest risk. And each has its own personality. Mount Baker puts out a lot of gas, but doesn't erupt very often. Neither does Glacier Peak, though one past eruption was 5 times as big as Mount St. Helens in 1980. Mount Rainier is the tallest mountain in the Northwest, and it isn't likely to blow its top. But it does have a lot of ice, which even small eruptions of hot gas and rock could melt, causing devastating mud flows. Mount St. Helens is still the one to watch. It's the most active in the chain, erupting once or twice a century on average. It's been torn down and remade so many times, the current mountain is only about 4,000 years old, compared to hundreds of thousands of years for other Cascade volcanoes, like Mount Hood. Hood's not far from St. Helens, but its personality is very different.
Mount Hood is not likely to erupt the way Mount St. Helens did.
Mount Hood has a history of venting gas and rock off of its sides, not huge explosions. That's not great news, though. Many people live on and around the mountain, and even small eruptions could cause landslides, explosions, and mud flows that destroy everything in their path. The rest of Oregon's volcanoes vary widely. Mount Jefferson has been relatively quiet for 20,000 years, long enough that it may be finished. South Sister goes off every couple thousand years. Newberry Crater more frequently, and like Hawaii's Kilauea, it can send rivers of lava far and wide. Then there's Crater Lake. Today it's a giant hole in the ground, but 8,000 years ago it was Mount Mazama, a mountain comparable in size to Mount Rainier. The explosion that leveled it? 50 times as big as Mount St. Helens in 1980.
Crater Lake produced the largest bang that we've had in the Cascades in the last 10,000 years.
That brings us back to the original question. Will one of these volcanoes be the next Mount St. Helens? It's a tough one to answer. Seth and his team aren't psychics, they're more like weather forecasters. They use a network of monitoring stations to keep tabs on what each volcano is up to.
Every volcano has its own sort of normal baseline, just like people. There's a range, of course, we know it's healthy, but within that, everybody's a little bit different.
Instead of heart rate and blood oxygen, volcanoes have earthquakes, ground warping, and gas bursts, even when they're not erupting. Comparing these vital signs to the historical record lets Seth and his team know if a volcano is acting normally, or if it's time to pay more attention. When Mount St. Helens woke back up in 2004, the observatory's measurements suggested it probably wouldn't blow like it did in 1980. And they were right. That doesn't mean Mount St. Helens is anywhere near done, though. Of all the volcanoes in the Cascade Range, there's a good chance the next Mount St. Helens will be Mount St. Helens. The forces that make mountains and destroy them, will continue to stir deep underground for a very long time. We can't stop volcanoes. We can't even say for sure when they'll wake back up. But by paying attention, we won't be caught off guard when they do.
Thank you, Jason. So during today's presentation, we're going to cover some of the topics and ideas that were presented about during that video. So the first topic is, why do we have volcanoes here in the Pacific Northwest? Secondly, what happens when volcanoes erupt here in the Pacific Northwest? What types of processes occur? And thirdly, how can communities, our communities, if we live here, live safely with volcanoes? Because I work as an educator, I have listed these goals also as objectives. So there's concrete things I'm hoping you're able to do by the end of this presentation. The first one is explain why we have volcanoes and where volcanoes occur on our planet. Second, to describe at least 2 types of processes that can occur at volcanoes when they erupt and the evidence that this leaves in the geologic record. Thirdly, to describe ways that volcanoes impact human communities and provide examples of strategies that can help people in these communities to live safely near volcanoes. Quite a bit, and here we go. We're going to start out with this interactive map, and I really like this resource. It's produced by the Smithsonian National Museum of Natural History, their Global Volcanism Program. And here at the Smithsonian, they track and compile all of the data about volcanoes across the world, specifically about volcanoes that are considered active or, as we learned during trivia, have erupted since the last ice age. Now, this map contains many different elements, and what we're going to do is we're going to try to understand patterns of where we have volcanoes to answer the question, why do we have volcanoes where we do, by looking at a map that shows time. So there's a timeline at the bottom. You can see the date here. Arbitrarily, I chose the date that Mount St. Helens had its large eruption in 1980. That's because, well, I dream about Mount St. Helens. And this timeline begins in 1960 and works its way to 2017. Now, there's different elements on this map to notice. First, there are blue circles, and these represent earthquakes. These earthquakes are only showing earthquakes that are between magnitude 5 and magnitude 9. If this map included every earthquake between magnitude 1 and magnitude 9 that occurred on our planet, we wouldn't be able to see much because there are many, many earthquakes. So these are the large earthquakes. Secondly, the red triangles represent volcanoes. Similarly to earthquakes, the larger symbol represents a larger eruption, and volcanic eruptions are measured using an index called the Volcanic Explosivity Index. It's also a Richter scale, so that means it's a logarithmic scale, just like with the earthquakes. So as you go from one number to the next, you're actually increasing by a factor of 10. Larger triangles mean larger volcanic eruptions. And finally, this last yellow circles are a way of tracking gas emissions. So volcanoes, I like to think, are sometimes elements that are burping up magma and gases from beneath the earth. And the most common gases emitted by volcanoes are carbon dioxide and water. Sulfur dioxide is not proportionally as much emitted, but it is a really good indicator of how much gas is emitted from these volcanoes. And so you can see the scale here. All that one needs to know is larger yellow circles is more gas. And sulfur is the gas that comes out of these volcanoes that smells, well, like sulfur or rotten eggs. So for folks that have skied up on Timberline on Mount Hood, or perhaps hiked up the volcano Mount Adams, you may have smelled the sulfur or seen yellow stained rocks, and that is because of this gas. So what we're going to do is we're going to play this video, and this video, the timeline is going to progress along the bottom, and what it's going to show is it's going to show an animation of where we have these 3 E's, as the animation is called: eruptions, earthquakes, and emissions across our planet throughout time. So it's really evaluating patterns on the Earth in the 4th dimension, including time. And as you watch this video, again, notice patterns. Notice if there's information that the video is representing that's familiar to you, and if there's anything that the video makes you curious about. I have pre-recorded this video with myself talking over it, so you'll get to hear me speaking to you with the video. Jason, if we'd like to go ahead with video number 2. Here is the animation of eruptions that have occurred around the world since 1960. Notice how the time advances on the bottom in the timeline. Notice first the abundance of volcanoes and earthquakes that occur around the world every single year. Every day there are volcanoes erupting around us. Also notice that there's a pattern to where the most common and frequent eruptions occur. Notice around the Pacific Ocean there is a ring, and that ring has many blue circles and red triangles, indicating earthquakes and volcanic activity. Notice also where some of the largest yellow circles, blue dots, and red triangles are located. I'm noticing the largest eruptive activity is around this ring around the Pacific Ocean. This ring is called the Ring of Fire, and it is the place where the Pacific Plate is sinking under other plates. We can also see lines of other volcanoes and outlines of other plates with smaller volcanic eruptions and earthquakes that occur on these other plate boundaries I'm highlighting. Okay, so many of the patterns that likely folks have noticed is the fact that the distribution of earthquakes and volcanoes on our planet is not random. And if we look at this map, which superimposes major earthquakes and volcanic eruptions in the past 10,000 years, we can see these patterns clearly outlined, which were visible in the last animation. Now, we do have volcanoes occurring in two different places primarily. One, we have situations where these are isolated volcanoes, which are called hotspots. And if you have questions or interest about hotspot volcanism, you're welcome to ask questions at the end of the presentation. Today, we're going to focus on a different type of volcanoes that form from a different process. And these are the volcanoes that form in what are called subduction zones. So to understand subduction zones, first we need to be able to conceptualize our planet as perhaps a hard-boiled egg. Lots of interior material with a very thin, brittle crust on the surface. And this hard-boiled egg is cracked, and the pieces on the crust on the surface are called the crust. And these pieces are moving around because the material underneath them is convecting or moving as well. It's because the earth is releasing heat, and much like a lava lamp, as things heat up, they want to rise, and then as they cool, they sink, and this creates cells of convection within the earth, and that drives the motion of plates on the surface. And you can see this map here that's like an elementary photograph, but notice how the plate boundaries match what we observed for the pattern of where we have earthquakes and volcanoes. And in fact, if we superimpose the plate boundaries on this map, we can see this really clearly. And there are certain places where the arrows show where plates are either coming together or moving in a certain orientation where we have certain types of volcanoes. And so I'm going to speak about these three basic means of plate interactions. So there's three ways that plates interact. Plates can first come together or collide, and we call those convergent boundaries or subduction zones. Plates can also move apart or divide, and those are called divergent boundaries. And then plates can slide next to one another, and those are called transform boundaries. And we can see places on our planet where these processes occur. So places where plates collide, if it is an ocean plate going into a continental plate, oftentimes you'll get a very deep trench. And you can see that with the convergent boundary over in the Philippines and off the coast of Japan. We have some of the deepest parts of the ocean are there. Places where the plates slide, one example is the San Andreas Fault in California, very well known. Places where the plates are dividing are places where the crust is very, very thin. And so on a map, these will be places where the water is not as deep. And we can actually see this if we take away the outline of the plates and we look on this map, we can see places, for example, the Backbone Ridge through the Atlantic Ocean, where we have a divergent plate boundary where the plates are so thin, it's very shallow and the water looks light blue. And so we want to think about for a moment, at which of these boundaries would we expect to find the most explosive volcanoes? So you can think about the animation that we saw where we had the largest blue circles, red triangles, and yellow circles. And then also thinking about the mechanism. So why? So we'll first give the answer here. The most explosive volcanoes are located at these places that we're focusing on today, the subduction zones or convergent boundaries. And I do want to spend some time on this. This is Plate Tectonics 101, because there are many misconceptions about why we have volcanoes where we do. So to do this, I'm going to use the example of the Cascadia subduction zone, which is the reason why we have the Cascades volcanic range here in the Pacific Northwest. So most volcanic activity on our planet occurs at plate boundaries, with the exception of these hotspots. Ask me about it at the end. And we said the most explosive volcanic eruptions occur at places where plates are coming together, convergent plate boundaries. Why is this? Let's use the example of the Pacific Northwest. So I have a star here where Mount St. Helens is because, well, it's just near and dear to my heart. And here, I'm going to outline in red the boundary between plates. So this is a boundary between two different ocean plates, the Juan de Fuca ocean plate and the Pacific ocean plate, and then another boundary between one ocean plate and one continental plate, the Juan de Fuca ocean plate and the North American continental plate. Now, a quick note about names. Whoever gets there first often is the first person to name in the Western tradition. And so these plates have many different names, and fragments and slabs of plates from the past have different names, depending on if one is working down in California or up in Oregon or Washington, and who discover this one fragment first. So I just want to say that the names don't matter, but the orientation and whether it's an ocean or a continental plate do. And these plates are moving in different directions. So the ocean plates are actually moving apart. That's an example of a divergent boundary. And then the continental ocean and continental plate are moving together. That's an example of a convergent boundary. So let's do a little bit of plate tectonics 101. So this is a very simplified cross-section of what is happening when one plate goes underneath another. Now, some things to notice. First of all, the scale of this diagram is off. I do not have a moment to illustrate it. And if we were able to illustrate it according to scale, it would not fit on this frame, because the scale of the size, for example, the depth scale here is so much greater, and then the width scale also. So we're squeezing this in, and this is a conceptual diagram. I just want to put that caveat out there. One thing to notice, the ocean plate is thin, and it's made up of generally heavier, denser material, so it often will sink beneath the lighter, more buoyant, and thicker continental crust. And we can see the arrows showing this plate motion where we have one plate coming into the other. Now, why do we have volcanism happening? That is because the ocean plate contains minerals. Those are components of the rock that contain water in them. And when these minerals go deeper underground, as they're moving like a conveyor belt down deep underground, there is more and more pressure, and that pressure makes it unstable for those minerals to, well, frankly, exist. And so the atoms that make up those minerals migrate, turn into other minerals, and water is one of the volatiles that is released in this process. I like to describe it as squeezing the sponge, and well, next time I'll flip this photograph over, because what happens is the water is squeezing out and it's migrating up versus down in this photograph. Now let me explain this a little bit more. Why do we have water in the minerals in the first place? Well, our ocean crust is starting at places where we have these divergent boundaries where magma is coming up to the surface, creating new crust. And when that molten material comes up and erupts as volcanoes on the seafloor, water gets mixed in. And there's some fancy science terms here if you want to use them in your vocabulary. And water becomes part of the structure of some minerals. And some of the most famous minerals that contain water are, for example, this rock called serpentinite, or the mineral is serpentine. This is lizardite is the specific type. It's very famous, shiny green, and one of my favorites. And this particular mineral forms by adding water to another mineral. So it's really adding the elements H2 and O into the mineral structure. And I put a photograph here so you can visualize what some of these mineral structures look like. They are three-dimensional structures of atoms. And when you add water to one certain type of volcanic rock, it creates this other type of rock. And in that way, water is stored in the mineral structure. As the subducting plate, the ocean plate, is going beneath the continent in these subduction zones, they're carrying the water that got in when the rocks were erupting closer to the surface on the seafloor. They're carrying that water deep down into the crust. And so scientists call this the seawater is entrained in the mineral structure. And I use this photograph of folks taking their suitcases because the water is getting carried away on the roller bags of some of these minerals like serpentine. And so when the ocean plate goes deep enough, as I was mentioning, the structure becomes unstable for the mineral serpentine to exist. It is just too much pressure underground, and that morphs into another structure. The atoms actually physically rearrange, create new chemical bonds, and some things have to go. There's just not enough pressure for everything to exist. It's like having a very crowded house party. I can't even imagine what that's like because it's been so long. Sometimes people just get bumped out, and the water is the thing that gets bumped out. What I do want to point out is that I love rocks, and this is an example of this process that happens beneath the surface, which people do not get a chance ever to see. There's too much pressure down there. We go from one green rock to another green rock. People call the second rock the Christmas tree rock because it often contains red garnets, and then the mineral there is green. That second rock is called eclegite. I just wanted to give you a little bit of some beautiful green colored rocks. So when the ocean plate subducts, the atoms that make up the minerals under great pressure rearrange to form new minerals that are more stable at the greater pressure. And this is all happening as our conveyor belt is bringing the ocean plate down. And how great of pressure are we talking about? Well, this is a chart of all of the types of categories of rocks that are formed that are called metamorphic rocks that form under pressure and temperature. And so pressure is on the y-axis, temperature is on the x-axis. And one of the rocks, the rock that we just saw, the Christmas tree rock, the green and red rock, is called eclegite. And you can see it is in the most extreme category for pressure. It is highest on the y-axis out of any of these categories. So there's some interesting, fun research being done about just how much water is in these ocean plates as they're going down. But the real question for us is, where does all that water go? So the water is getting trapped in the minerals, and then it goes down, and then we're saying it gets squeezed out. What happens to it? And so here we go back to this elementary style diagram, and we see the blue droplets representing water coming up from the ocean plate. And when that water interacts with the continental plate material above it, so that is rock of the continent above it, it's much like putting salt on an icy road. It changes the melting temperature, and it causes the rocks to melt at a lower temperature than normal. And when those rocks melt, they become more buoyant than the surrounding material, and they rise. And that is the mechanism for why we have molten material coming up to reach the surface underneath volcanoes. Now, it took a long time to explain that because I find that many people do not quite have a sense for the entire cause and effect of this phenomenon. And so we took a little time there. Now, a classic diagram shows this, where we have our ocean crust growing at the spreading center on the left. The ocean crust is getting pulled down because the rocks that make it up are actually really heavy. So when the serpentinite goes to eclegite, that's an even heavier and denser rock, and it pulls the slab down even more, and that pulls the crust away from the spreading center, causing more magma to rise there. So we get the creation of new ocean crust, the subduction of the existing ocean crust, and all of that causes the melting of the continental crust. And the melting of the continental crust comes up and expresses itself as the volcanoes, such as this diagram, which emphasizes the plumbing under Mount St. Helens. How lovely. So let's do a little pop quiz. Let's go to the opposite orientation in Japan, where we similarly have an ocean plate going underneath a continental plate. And this is straight from the scientific jargon, but I want us to notice the things that we've now learned about. So first, we have fluids. That is the dehydration of the slab. That is the water getting squeezed out. Again, next time I'll flip this photograph so the water's going up. Secondly, we have this, what's called partial melting, or the changing of the melting temperature. And that, you can see the arrows is pushing that plume of red molten material up towards the surface. And then we also have the arrows dragging down the ocean crust here, which are representing the change from the minerals going from a more lightweight serpentinite to a more heavier rock, eclegite. Let's look at this one more time with an even more complicated diagram. Testing everyone here. So again, this is the orientation of Japan style, where we have ocean crust going underneath continental crust. And what are some of the words here that we can start to recognize? Well, first of all, this is the direction of the subduction. I see we have the volcanic front and the magmatic arc. So notice where the magma actually comes up. It's when the plate is getting deep enough that the water can come out and that's what causes the magma to rise. So notice the difference between the distance between the trench on the right side here to the volcanic front is actually quite far. So here in the Pacific Northwest, our trench is way off the coast, but our volcanoes express themselves still, oh, I don't know, 30 miles inland. Don't quote me on that number. And again, we have these arrows representing the dewatering of the slab, which we learned about. And then we also have these words now that might become familiar from that other diagram: eclegite, facies, just as a term for a group category of rocks. Blue schist is another really colorful, beautiful rock that forms at very high pressures. And so one other factor that controls where we have volcanoes is the fact that this molten material, when it's coming up, has to navigate around the pre-existing structures in the crust. And this was one of the trivia questions that was highlighting or asking about how scientists are, what kind of evidence scientists are using to understand why Mount St. Helens is slightly further to the west than Mount Rainier. And you can see in this diagram, it actually makes a little triangle. MSH stands for Mount St. Helens here, MR stands for Mount Rainier, and the little triangle for MA is Mount Adams. And you notice there's different blobs here. Well, this research was done using primarily seismic waves, so a way of ultrasounding through the Earth's crust and imaging what is solid and what is more molten underneath, what is colder and what is warmer. And by taking these very detailed, high-resolution seismic surveys, scientists are able to come up with these beautiful CAT scans, or three-dimensional diagrams that show some of the blobs. And the resolution isn't amazing. We can't get down to much more than big blue blob or slightly less big blue blob. But it is very exciting. This is new technique for understanding what happens in our Earth. And this is new as of the last 10 years. Tomography is very, very exciting. And so you can see here that there are some blobs that the magma of Mount St. Helens needs to come around. And there's many different things on these diagrams that we've spoken about. You can see the JDF stands for the Juan de Fuca ocean plate subducting down, and then those little black arrows are representing the water coming up, and you can see all of these yellow blobs underneath the surface in the gray diagram to the right representing the different bodies of more molten material rising. And notice, again, the material has to go around this one big blue blob in the center, and we'll zoom in here. This big blue blob is the what's called the Spirit Lake batholith, which is just a harder chunk of rock that intruded earlier. And so that is part of the reason folks think that Mount St. Helens and Mount Adams are a little bit off of the straight and narrow course, because the magma needed to go around this more resistant material. So this is another control on the location of volcanoes, but this is a control on kind of, plus or minus 10 miles. But the larger control on why we have volcanoes in this Cascades Range is because we have subduction. We have one plate going underneath another. And so I just wanted to point this out because it's exciting new science. This paper was published, I think, in 2018. And they write, quote, crustal structures are equally important in controlling magma ascent and defining the spatial distribution and compositional variability of the erupted material, end quote. And this, my friends, is why we have such variability in some of our volcanoes. For example, Mount St. Helens as compared to Crater Lake, as compared to Newberry Crater in Oregon. Some of the reasons for both where we have the volcanoes located and then the compositional variability, which we'll get into, which affects what type of eruption is possible, can be tied to what the magma has to travel through to get to the surface. So that covers our first little section. Why do we have volcanoes in the Pacific Northwest? Second topic, what happens when volcanoes erupt in the Pacific Northwest? Here we go. So I'm going to go through this, again, an elementary diagram so that we have a visual in our head for some of these processes. This diagram I actually really like. It's created by the USGS. And there's nothing wrong with simplistic diagrams. They just can be limiting sometimes in the scale because the graphic designers are trying to represent so much in just an 8.5 by 11. So let's focus on these different processes that are possible. First, lava flows, ashfall, volcanic gases, landslides, lahars, pyroclastic flows. And what we're going to do is we're going to use the example of Mount St. Helens, of course, to speak about some of these processes. So I'm going to show you some photographs of what happened at Mount St. Helens to give us some context for what's possible, because Mount St. Helens is representative of the volcanoes here in the Cascades Range. So to just remind us what happened to Mount St. Helens, there was a major eruption just 41 years ago now. May 18th is the anniversary. It's coming up. Celebrate the 41st. And these are photographs taken from almost the same location, showing before and after the changes in the landscape. So you can see many things changed, including the shape of the mountain. And when Mount St. Helens erupted in 1980, many of the processes that we just went over occurred here. So we're going to zoom in on some of those processes. First thing are lava flows. And this is one process that did not occur during the 1980 eruption. But if you fly over or hike up the back south side of Mount St. Helens, you will see that the side of the volcano is actually comprised of many large lava flows. And these lava flows happened many hundreds of thousands of years ago, but it takes plants a long time to recolonize on raw lava. And so these flows are still visible from space and make the climb particularly arduous if it's not covered with snow, because it's lots of climbing over one boulder, climbing down the boulder, and climbing up the boulder on the other side. Now this photograph, it's a little grainy, looking into the crater of Mount St. Helens, shows some of the different colors, and these colors all represent rocks that were erupted at different periods of time. In many of these different eruptions, some of these were lava flows or lava dome eruptions, and you can see that the present cone of Mount St. Helens, this is again a cut into it because the eruption exploded out the side of the volcano. So now we can look into the wall in cross section, and we can see that the volcano is comprised of many, many different eruptions that created, well, it's not very obvious in this photograph, but to me, I'm just amazed at the delightful range of colors in this photograph. For most folks who don't study geology, this might not look colorful, and you might say, wow, what a boring photograph of gray rocks. But I see an amazing array of reds and dark grays and light grays and yellows and tans. Not green rocks, though, here. Another process that occurs at volcanoes, of course, is ashfall. And ashfall can dramatically impact communities near volcanoes, such as this photograph taken just north of Mount St. Helens, showing the ash coating the field like snow. And then also this ash can accumulate in the geologic record. So with enough time, you can get layers of ash that can accumulate and turn into rock if they go underground deep enough and there's enough water and fluid moving through to mineralize or turn it into rock. But also these layers can just form some of the unconsolidated material on the surface, and this can affect what type of plants can grow, and also much of this debris, if it does not turn into hard solid rock, can be very easily eroded. So you can see this big cut here, perhaps along a river, can contribute to flooding and debris flows down the river. And we call this in the geologic record, the layers of ash are called tephra layers. And this is a photograph of some of the tephra layers famous at Mount St. Helens. For example, the Y layer, I think that it is called that because Y for yellow. Don't quote me on that. But some of these layers, because every layer in every event that created ash had a little bit different chemistry of what was coming out of the volcano, it's possible to track and date and also correlate between different ash layers. So for example, layers of ash erupted from Mount St. Helens were found up at Mount Rainier and used to track and see the extent of the eruption that occurred. Another process that happens at volcanoes is volcanic gases, and this can affect people if you're very close inside the vent of a volcano. It can also stain the rocks yellow. As you can see, these yellow-suited geologists standing in front of yellow sulfurous rocks. This is measuring gases in the crater of Mount St. Helens. Another process that is relatively common at these volcanoes and not quite understood well before the May 18, 1980 eruption of Mount St. Helens are debris avalanches, or more commonly called landslides. And why are landslides so common from these volcanoes? Well, these volcanic cones for our Cascade volcanoes are often comprised from one eruption stacking on top of and then exploding, and then stacking on top of and exploding successive layers of material. So there might be a big explosion that breaks everything up, and then some bubbling lava or a lava dome eruption, and then another stacking of more material, and then a big explosion that breaks everything up. And so our cones that we see are actually not as stable as we might believe. And so for the side to come off in a massive landslide, like it did in the 1980 eruption of Mount St. Helens, is actually quite common. And part of the reason the slope of Mount St. Helens on this one particular side, the north side, became so unstable was because magma was rising beneath the volcano, cracking and breaking the rock. And that led to even further instability in an already relatively unstable edifice. I love this series of photographs. These are taken by a man named Gary Rosenquist, who was out camping near Mount St. Helens, was out to photograph the mountain on the day that it erupted, not knowing the eruption was going to happen. It was just a clear, beautiful, sunny day. He accidentally moved his tripod, so Mount St. Helens was not centered in the frame, and then, by gosh, the volcano erupted, and the eruption itself was centered in the frame instead of Mount St. Helens. If he had Mount St. Helens centered, the sideways eruption would have been cut off in these photographs. So I just am so grateful for that slip of fate that he happened to knock his tripod to focus and center the sideways eruption. What do landslides do when they hit the ground? What kind of deposit is left in the geologic record? And how can one recognize signs of a landslide that has occurred at other volcanoes? Well, when Mount St. Helens erupted, the landslide was particularly large and it left a very distinctive deposit. You can see that here. I describe this to the students as lumps and bumps in the landscape, what are called hummocks. And you can see these hummocks have very steep relief, steep sides, and it really is debris that's scattered across the landscape. And the reason why the deposit isn't smooth is because when the landslide's coming down, the material that's coming down in the landslide are chunks of lava flows, chunks of former eruptions, broken and crumbled rock. It's a mix of material that's all somewhat broken. Some chunks are intact, and that leaves a scattered mess across the landscape. When I work with students, I ask them to imagine taking an Oreo cookie smoothie and dumping it across the table and thinking about the lumpy and chunky deposit that's left behind if you had a bunch of stuff in that smoothie, including bananas and pieces of Oreo cookie. And so these hummocks are actually seen at other volcanoes in the Cascades, such as at Mount Shasta. And I love this photograph because these hummocks were formed a very long time ago, 300,000 years ago, but they're still there. And so one might go to Shasta and say, wow, are these all other small cinder cone volcanoes surrounding the volcano? But after Mount St. Helens erupted in 1980 and the hummocks were seen there in the landscape, it became clear that's what these were. Now, a quick pop quiz. How many times greater do you think the debris avalanche at Mount Shasta 300,000 years ago was than the May 18, 1980 eruption of Mount St. Helens? Take a moment. And these hummocks have had a moment to weather, so they're very rounded. Well, the answer is that it was 22 times larger. So for the massive scale that we saw at Mount St. Helens in 1980, it's very possible and probable to have even larger events happen at some of these volcanoes. And these hummocks are visible if you drive on I-5 south through Northern California, through Redding and Shasta. And I think there are still signs on the side of the road that say mysterious mounds. But now, being more informed, you have a new perspective to look at these lumps and bumps in the landscape around volcanoes. Another process that happens at volcanoes are called lahars, and lahars are an Indonesian term for debris flows. And these occur when the snow and ice that's on the mountains mixes with all the ash and debris and flows downstream in the river channels primarily. And these debris flows that occurred at Mount St. Helens were substantial. They flowed for over 12 hours after the eruption, and they went tens of miles from the volcano, and they left and buried homes and bridges. You can see in some of these photographs. The photograph in the bottom right corner shows a very large boulder, giving an example of the scale of material that can be moved by these, and then also the photograph in the center that shows just how high this debris came through. People describe lahars as rivers of concrete, and they are particularly dangerous in the fact that they can go so far from volcanoes because they, again, are moving, traveling down river valleys. So, for example, at Mount Rainier, there are historic lahars that have traveled over 90 miles from the volcano into places like Kent, underneath some of these suburbs of Seattle. And so if a large lahar debris flow was to occur at Mount Rainier, it would pose significant risk to the communities there. And in fact, today there's a new program for communities that are inside lahar hazard areas to do lahar drills. I'm happy to speak about that more at the end of the presentation. And so the record that's left behind by lahars is a deposit. You can see these people standing amongst it of a mix of boulders and material debris and ash, and often very flat. So you can see this flat deposit filling the river valley here. Another process, final process we'll speak about that occurs at volcanoes is called pyroclastic flows. These are, instead of the eruption column of gas and ash going up into the air, these are gravity-driven flows, and they can be so powerful that they can go up and over ridges, moving at incredible speeds, incredible temperatures. It is very deadly. Luckily for us, we don't have communities of people that live so close to our volcanoes here in the Pacific Northwest that we would be in danger of pyroclastic flows necessarily. And at Mount St. Helens, this is a photograph of a pyroclastic flow that occurred after in a subsequent eruption from the 1980 eruption. And this is the type of deposit that's left behind by pyroclastic flows. The ones that occurred at Mount St. Helens were pumiceous or erupting pumice, that is that rock that floats. That's not made of styrofoam, but it floats because there's so many vesicles or pockets from gas when that rock cooled down. And I love this photograph of a geologist holding a gigantic rock, but it really is just a large piece of pumice. And it just looks really impressive to me. So with so many different volcanic processes happening, all of these types of processes are possible at all of the volcanoes in the Cascades. And depending on, again, the structure beneath the surface, what the magma has to go through to reach the surface, the volcanoes will have a unique personality and eruptive style. But a question that's commonly asked is, why do we not have eruptions in the Cascades that look more like Hawaii? So I want to focus in on that for a moment. So explosive eruptions, which are the classic Mount St. Helens 1980 eruption, not a flowing lava eruption, these occur because of two primary factors. One, you have trapped gases, and two, the magma itself is compositionally less viscous. Wow, it's late in the presentation to use such big words. Okay, explosive eruptions because of trapped gases. Think about it as a soda. What traps the gases? Physically, the gases are trapped by the structure of the magma. So if the magma is sticky and has many things connecting it, the gas cannot escape or just fizzle out, and it builds up pressure, and that leads to these big explosions, such as what happened at Mount St. Helens on May 18th, 1980. Now, explosive eruptions also occur because of the composition of the magma, and that contributes to its what's called viscosity or resistance to flow. And so what determines the type of lava that's erupting from these different volcanoes? Notice the one from Hawaii and the one in comparison to Mount St. Helens. I like to describe the Hawaii style lava that comes out as being runny like honey. And then the type of lava that has come out of Mount St. Helens, especially what came out of Mount St. Helens in the 1980s and in the 2000s, is sticky like Jiffy peanut butter. And the viscosity of this magma is due to the chemical structure. So the basic building blocks of most rocks on our planet are these little three-dimensional pyramids that comprise of 4 oxygen atoms and 1 silicon atom in the center. And these little tetrahedra can be floating isolated on their own. And when we have isolated tetrahedra, this means that we can have a viscosity that's very low viscosity. So it means the magma is very easy to flow. The lava is very easy to flow. And this gives us our runny like honey lava. But these tetrahedra can also be linked together. They can be linked in chains, as this diagram shows. They can be linked in double chains where you get these rings. They can be linked in sheets, or they can be linked in 3-dimensional structures. And the more you link them, the more clumps of linked things you get. And I like to describe it as maybe a chunky minestrone soup. All of a sudden, it's not going to pour as smoothly. There's chunky stuff, and this inhibits the ability for gases to escape, and also it prevents things from flowing easily. And so that builds up pressure, and that leads to this sticky lava and also these explosive eruptions. So again, just highlighting the difference, we have our runny like hot runny like honey lava, which compositionally is called basalt. And then our stickier lava compositionally is called dacite, rhyolite, or other names. A quick 101 in geology: for many types of rocks end in ITE. So dacite is one type of rock. So we're going to watch a video here to give us an example of this type of lava extruding. This is going to be video number 3. It's showing a time lapse of the lava dome growth at Mount St. Helens between 2004 and 2008. There was a camera on the east side of the crater, and it was looking into the crater, and you're going to see rock just magically coming out of the volcano. This is something geologists drool over. I'm really grateful for the work of USGS scientists who were able to put a remote camera up there, so they were able to capture this footage without endangering anyone's lives. And the eruptions that are happening are relatively safe during this time because they were contained inside the crater of Mount St. Helens. But there is also danger involved because the scale of what you're seeing is actually quite large. These whaleback spines get to be above the size of the Empire State Building. As you watch this video, think about what you notice and what might surprise you and what makes you curious. You will hear my narration in the video. And Jason, you're welcome to play video number 3.
This video shows a time lapse of lava dome growth between 2004 and 2008 from a remote camera stationed on the east side of the crater of Mount St. Helens. This video is produced by scientists at the U.S. Geological Survey. In the bottom right corner, we can see the date that each photograph was taken. This remote camera captured a photograph multiple times a day. Notice the large whaleback spines erupting from the lava dome like toothpaste coming out of a tube. Lava domes are formed from viscous magma erupting non-explosively onto the surface and piling up around the vent. There is not enough gas or pressure in this lava to erupt explosively. This lava is too thick and sticky to flow very far, so instead it piles up thick and high around the vent. This was an exciting time for Mount St. Helens, and even more exciting for scientists and viewers like us that could watch all of this incredible activity within the crater. By 2008, the eruptions of this eruptive period had ceased. Both the glacier and the lava dome are colored in gray, so it may be difficult to distinguish which is which. Look for the cracks in the surface of the glacier and watch as the lava dome extrudes in the center of the crater. Watch also as it squeezes the glacier against the crater walls, forcing the glacier to move quickly. Finally, the glacier comes together. Special thanks to the USGS scientists for putting together this animation. This video shows the growth of the crater glacier at Mount St. Helens between 2005 and 2012. The photographs captured the growth of the lava dome between 2004 and 2008, as well as the continued growth of the glacier after 2008. Here we see the different lava dome eruptions of 1980 to 1986 and 2004 to 2008. The date the photographs were taken is in the top left corner. These photographs were taken by a remote camera on the northwest flank of Mount St. Helens. Watch the glacier move down the sides of the lava dome. Notice both the lava dome rapid growth and buildup, as well as the rapid movement of the glacier. Notice how dark colored the glacier becomes in the summertime with the rocks covering it, and then how light it becomes during the winter when it becomes again covered with snow. As the glacier moves to advance to the front of the crater, its rate of movement slows as it reaches a more shallow crater floor. The east and west arms of the glacier wrapped around the lava dome and finally connected in 2008. This was an exciting time for scientists as we recognized we had the first donut-shaped glacier. After 2008, the lava dome growth ceased, but the glacier continues to advance down the crater floor. Scientists continue to monitor the growth of this glacier today. As the glacier moves to the front of the crater, it also becomes out of the shade of the crater walls, and thus begins to slow its growth as it sits more fully in the sun. This video was produced by the U.S. Geological Survey, Cascades Volcano Observatory.
Great, so we just watched a series of time-lapse videos that showed the growth of both the lava dome and then the glacier that's grown around the lava dome at Mount St. Helens from 3 different perspectives. The first one was from the east side looking in, the second one was looking down, kind of bird's eye view, and then the third one was looking from the west side of the crater. And I hope those 3 give you some sense for what it means for volcanoes to be erupting in a different style than Hawaii. So that concludes our second section. What happens when volcanoes erupt in the Pacific Northwest? Of course, there's much more detail, but we're going to move on to our third part of our presentation here, which is how can communities live safely with volcanoes? And so I want to just highlight a couple of ways that I feel we can work well as communities to live safely with our volcanoes. First idea is to change how we conceptualize these volcanoes in the first place. So the indigenous people that call this place home and have lived here since time immemorial have oral and cultural traditions that speak about the fact that the landscape changes. When we use names like Mount St. Helens, these names were gifted by someone who was pointing fingers from a boat far away at landforms that stuck out and was gifting these names based on sponsorship, much like we have sponsors for sports events. And so perhaps by bringing awareness to some of these indigenous stories and names for some of these landforms, we can have a little bit more, a deeper understanding and an understanding that reaches back further in time about what types of processes are possible in the landscapes here. At Mount St. Helens, people before the May 18, 1980 eruption had used Mount St. Helens as much of a vacation home, similar to the way Mount Hood was very developed with a lodge, a Boy Scout camp, and this photograph shows folks recreating out on Spirit Lake in 1980, I think it was taken. And so by, again, through talks like this, through the work of OMSI, bringing awareness to the fact that these volcanic landscapes are continually changing can help us be more comfortable with the change when it happens. And that video that we started with highlighted some of the volcanoes that are more likely to erupt. And so the scientific research can help with that. All in all, we are living full force in the shadow of these volcanoes. This photograph from looking from the Portland airport with Mount Hood in the background. And on some level, there's an opportunity for education that doesn't exist for other types of natural hazards and natural processes, because these volcanoes are visible to us on a clear day here. And so we can speak about them and we can imagine some processes happening, because it's not only processes that are happening underground. And when Mount St. Helens erupted, the fact that the volcano erupted in May 18th, 1980 on a clear day, the fact that we could take remote time-lapse photography of successive eruptions gives us more perspective for the types of processes that can happen at these volcanoes and the way the landscape can change. Secondly, by being more aware of the hazards and risk associated with different eruptive processes, our communities can be more prepared. So let's go back to one of our trivia questions. Which of these volcanic hazards that we spoke about historically has resulted in the most human fatalities? Out of all these processes, which one should we be the most concerned about for the greatest number of people? And the most deadly hazards historically have been for a couple of reasons. First on the list are the secondary effects. So when people are displaced when landslides, lahars, and other processes actually wipe out communities, and then people are left without crops, for example, that can lead to starvation. When volcanoes erupt, the earthquakes associated with eruptions can cause tsunamis. And then top on this list are the lahars, or the debris flows and mud flows. And you can see mud flows are most common on this list. So even in Vesuvius and some of these other places that might be less familiar. Another way that we can live safely with volcanoes in the Pacific Northwest is to support initiatives that put money and funding for science and monitoring to inform emergency management and policies. So different ways that science can help. Computer models are now used to predict where ash will go different times of day, different times of the year based on models of prevailing winds. We spoke a bit about what type of research is being done using these seismic waves as an ultrasound to think about what's happening beneath the crust, which can help us understand if a new volcanic event was to arise in a different place, where that might be, why that might happen. Pictured here, you can see Indian Heaven, which is a recent volcanic field, and that's a little bit more complicated. You can ask me about that in the Q&A. And then also, scientists take all of the geologic evidence, what's preserved in the geologic record that we saw from all of those different processes, such as the layers of ash, to understand what is possible. So if Mount St. Helens erupts ash, how far can it go? If lahars flow from Mount St. Helens, where do they go and how far can they go? So all of these models of what is predicted for the future are predicated on what has happened in the past. And the only way to know about the past is to put on one's hat, carry a rock hammer, take samples, do laboratory analysis, and really study the geologic record that's there. And the further back in time we go, the more difficult it is to decipher. And it takes many, many tens of years of people working together to understand these pictures of what's possible. And this is a photograph of a hazard map. If you live in the Pacific Northwest and you have not seen this map before, I encourage you to go to the U.S. Geological Survey to learn more. This is an important piece of public media and outreach. There is a map for each of the volcanoes that highlights the near volcano and further from volcano hazard zones that would most likely affect communities living nearby. And you can see this map ends right north of Vancouver, Washington, and then borders into Portland. Finally, collaboration between scientists, emergency managers, and other stakeholders can help our responses to volcanic eruptions and processes be more streamlined and smooth. So I'm hoping by the end of this evening tonight, you are now able to explain a bit about why we have volcanoes where we do on our planet. You're able to describe perhaps two types of processes that can occur when volcanoes erupt and the evidence that this leaves behind in the geologic record, and the ways that volcanoes impact human communities, and some examples of strategies that can help communities live more safely with volcanoes. And I want to end with this beautiful photograph here to remind us that volcanoes love us as much as we love them. This is a picture of the lava lake in Kilauea this past year, I think in 2019, and it formed a smiley face, which is of course on the wall in my office. And I took this slide from my beloved coworker and mentor who's taught me so much about volcanoes. And she likes to give always a big shout out to volcanoes during her presentations to thank them for all the things that we use in our daily lives that come from them. So credit to Sonia Melander here, cheese being one of the things. Finally, a big thank you to OMSI for hosting me for this presentation. I am excited to answer questions that you all have, and I hope that this talk gives you some perspective to look out at the landscape, to recognize features and patterns of the landscape, and to be more informed as community members, to affect policy that can hopefully contribute to more understanding of these volcanoes and what's possible. Thank you again.
Thanks so much, Gina, for that presentation. I really appreciate just how thoughtful you are in the way you use metaphors to explain complex scientific things, as well as the credit you've given to so many others who've come before us to help us understand the mountain. We have a few questions, and I also want to remind anyone who's watching at home that you can continue to put your questions in the YouTube Live or the Facebook Live chat area, and we will ask them to our presenter here. But let's see, to get started, one question is thinking about some of the more recent volcanic eruptions, like in Iceland. Do you know if scientists were able to predict or anticipate that? Was there any advance notice, or did that kind of come out of nowhere?
So every time a volcano erupts in our modern techno society, we have more information for the early warning signals for that eruption. And so back in 1980, there were some signals, for example, earthquakes, but our ability to detect earthquakes to the scale and frequency that's necessary to really know if it's a rumbling or if it's a rumbling that could lead to an eruption, the resolution wasn't there. And so every year we're moving towards having higher resolution equipment and the ability to kind of keep a closer watch for some of the signs. And some precursory signs of eruptions often are what are called magmatic earthquakes, where that is from the magma moving, cracking, and breaking rocks. Other signs, you can see ground deformation, that is change in the shape of the volcano as the magma is coming up. And those were two things that very obviously happened in Mount St. Helens. But for example, in Mount St. Helens in 1980, that eruption, one of the first earthquakes when the volcano was really starting to rumble was caught on a seismometer up at the University of Washington, which was pretty far away. And scientists hurried to put a seismometer much closer to the volcano. City of Mount St. Helens has the most equipment of any of the volcanoes in the Cascades. That being said, there's a discrepancy on which volcanoes have more equipment than others, and often historically it's because that volcano has erupted. So I'm not as familiar with what the monitoring is in Iceland, but I do know here in the Cascades that there are certain volcanoes that have much more equipment on them than others, and that is a little bit of a historical bias based on which volcanoes have been most active in the present time. But overall, the question that anyone who studies volcanoes always gets is, when is the next eruption? And what I always tell the students is, you better hurry up and become a scientist to help us answer that question.
Totally.
Thanks.
It could be tomorrow, or it could be years and centuries. One question that you actually prompted earlier was about hotspot volcanoes. Can you tell us a little bit about what hotspot volcanoes are and how that maybe differs from the kind that we occur at subduction zones, like in Cascadia?
Sure. So subduction zones, we learned the mechanism is one plate going underneath another, specifically an ocean plate with minerals that contain water going down at depth, and the water coming up and melting crustal material that otherwise would be really difficult to melt. Before the 1960s, there wasn't a hypothesis of plate tectonics to support this, and there actually were many people who did not believe that volcanoes were formed from material that was completely molten. It was kind of like a solid state pressure process. So that was a theory called granitization, and that's now feels like since long away, but it is the generation of, for example, my grandparents, where that was a theory that was in contention with plate tectonics equally on the table. So our understanding of the processes that happen has really, really grown tremendously in the last 50 years. Hotspots are places where the material that's molten, for some reason, we have material that's rising like a lava lamp, and it is breaking through the crust, not at the plate boundaries. So Yellowstone is an example that is through the center of this North American plate. And then Hawaii is an example of a place that's busting through the Pacific plate. And why do we have material coming up at those places? We don't have this water that's changing the melting temperature, and we don't have the stretching of the crust that happens at spreading centers. A quick note about that: when you stretch the crust, that leads to a decrease in, there's less pressure on the rock below, and that's what causes melting and the magma to rise. But hotspots are different. So what causes the melting? Why do we have material rising up? And more we're able to use seismic waves to look deeper and with higher resolution beneath the crust to ultrasound our planet. And more we're being able to see structures, really blobs that are deep down in our massive Earth. And current hypotheses about why we have hotspots where we do is that they are potentially places where you have fragments of plates, where heat is like building up on the boundary of the outer core and the mantle. And then that rises as these big plumes, and that goes all the way up and busts through the crust to the surface. So generally, the short answer is hotspots are a form of volcanism that is much a deeper and hotter source than the processes that we get happening at the boundaries of plates. But it's still, if there's geologists in the audience, we could debate this for a long time.
This might be another one of these things where, like, 40 years from now, there'll be some science pub saying that, Okay, so here's another question. What are the dangers from Mount Hood? I'm thinking about that slide that had the vents on the side, and maybe some people are thinking about their favorite vacation places or, popular tourist destinations. Like, should we be worried about that? Would you buy a vacation home on the flanks of Mount Hood?
I actually have spent more time at Mount Hood this season than I have in the past. So it's been really fun to play. I don't go to Mount Hood often because I spend most of my time at Mount St. Helens. So I've got to know Mount Hood a little bit more this season. And we get students also visiting Mount St. Helens saying, why would I want to visit here? Is this volcano going to erupt? And we are at a point in the science where we can recognize some of those precursory signs to know enough whether an eruption is possible. And so the U.S. Geological Survey has, after the eruption of Mount St. Helens in 1980, created a network of folks who are studying the active Cascades Range. And I didn't speak about this, but there is the Cascades Volcano Observatory that keeps track of all of our volcanoes here. And they have an alert warning system for each of the volcanoes. And for them to change the alert warning system to go from green to orange is a really, really big deal. So it means that there's enough evidence to warrant that, and different color levels can mean that, for example, like an evacuation is necessary. And so I'm imagining, I've heard an interview with Seth Moran, who heads the Cascades Volcano Observatory for the USGS, and he said if Mount Hood ever becomes active, it may not erupt, but it may have enough signs that look like an eruption. And if we have to tell everyone in Portland not to go to Mount Hood for a couple of years, I don't know. I think that would be really difficult to control. So that, to me, I'm grateful that Mount Hood isn't rumbling right now, because it's used by so many people for access to the healing power of being in the Alpine. And it is one of the volcanoes that is more developed with ski resorts right up the flanks. I mean, I'm always awestruck when I have the opportunity to ski there. So all in all, Mount Hood has quite a bit of monitoring equipment on it. And there was actually, I included in some links following this presentation, some information. The USGS recently installed more equipment on the volcanoes, so you can learn exactly what's going on. Everything that the USGS does for monitoring these volcanoes is put out to the public. They've got a great social media page where they post things, and they also are constantly updating their website with reports. So it is not something to be concerned about if you know the agencies to follow to be most informed. So if I want to know what's happening with the volcanoes in the Cascades Range, I'm going to go to the Cascades Volcano Observatory that is straight from the source. If I want to know what's happening at Yellowstone, I go to the Volcano Observatory that's out there. Hawaii has a volcano observatory. So there are networks, Alaska Volcano Observatory, AVO, and you can sign up to get little alerts from them if you like your phone to ping and hear about the very obscure eruptions that happen almost every day up in Alaska. Thank you.
So we got a couple more questions that just came in from virtual visitors. One is, which volcano flow created the Columbia Gorge scenic area? And I think there's probably multiple ways you can answer that question. But yeah, how does that maybe differ from the volcanic stuff we have going on in the actual Cascadia crest?
Great. Oh, I'm glad this question came up. So the big layers of dark colored lava that we see in the Columbia River Gorge are from volcanoes, but they are so tremendous in scale. It's larger than the scale of anything that one of our cone-shaped stratovolcanoes here in the Cascades could create. So those come all the way from the hotspot over in Yellowstone. So only a hotspot could generate that type of scale of an eruption on a continent. Under the ocean floor, we have eruptions happening all the time. But in general, the scale of what we see in the Columbia River Gorge, which is lava flow on top of lava flow on top of lava flow, like tremendous amount of lava. That is not really possible from the volcanoes that we have here. If you look on the map of the scale of how far we get lava from, for example, down in Oregon, like the Sisters, or other places. Mount Shasta has big lava flows. The scale does not compare. It's an order of magnitude, multiple orders of magnitude different in terms of volume. And that's because that hotspot is coming, it has this really, really deep source, and it's coming up, and it's still an active hotspot there in Yellowstone.
A lot of runny honey.
A lot of runny honey. Thanks.
I was paying attention.
Of honey.
Okay, time for maybe like 2 or 3 more questions. Can you talk about volcanoes in Portland at all? That's a question just popped up from online.
Sure. I will say that I am helping to coordinate some field trips for the public. There is a big meeting of geologists that happens every year, and it happens in different places around the country, put on by the Geologic Society of America. And I'm helping to coordinate some field trips that are open to the public. This meeting is in October, and we're hoping to do some in-person field trips. So one to Mount St. Helens, one to the Columbia River Gorge, and then one to some of the parks in Portland that are volcanic, such as Mount Tabor and Powell Butte and Rocky Butte. And those are a little complicated. So I gave you all a little bit of the 101. Everything in life is more complicated if you go into it. The volcanic field of Portland is interesting. It's the only city with an active volcanic field in its city limits, I think. And the volcanoes are part of what's called the Boring volcanic field. Boring is the name of a town on the way to Mount Hood from Portland. It's not boring. It's actually really enigmatic why we have this volcanic field here. But again, I think it's tied to the structure beneath the surface. So the Boring volcanic field, Portland, is a little bit to the west of the Cascades arc, but it's still on this line with the subduction. And so there's some thought that the reason it exists where it does and to the scale of where it does is because, again, of these blobs of material that make up this heterogeneous crust that the molten material is coming up through. It's not a great answer, and I appreciate the question. I'd like to learn more about it. But if you're interested, these in-person field trips with the Geologic Society of America annual meeting in October, you can reach out to me via email on the contact information that's listed.
Awesome, thank you. So for our last question, if you could just take a minute and tell us a little bit about educational programs or resources available through your institution, Mount St. Helens Institute, that people can look into if they want to learn more about volcanoes in Mount St. Helens.
Sure. The Mount St. Helens Institute is a nonprofit organization, and we offer a diversity of programs to connect people to the landscape. So we do guided hikes up to the summit. We have permits to go on this side of Mount St. Helens into the crater. They're called itch hikes, into the crater hikes, or hikes to get an overlook of the glacier. And after Mount St. Helens erupted, the area around the volcano was preserved as a national volcanic monument with very restricted access in certain areas that were most impacted by the eruption. And at the Institute, we have permission to go off trail into places that are not accessible to the public. So I think that's one of the benefits of the Institute. If you are an adult interested in a guided hike, that would take you somewhere you wouldn't be able to necessarily go. If you work with a school as a teacher, or maybe you're a student and you want to come on a field trip and be able to do some hands-on science practices in places that the public's not allowed to go, that's some of what we offer. We also do offer a speaker series, a lecture series that can get real nerdy real fast about Mount St. Helens. It's called Views and Brews. And for more information about the Mount St. Helens Institute, you can follow the Institute on social media and also check out our website or send me an email, and I'm happy to connect. but it really is an organization whose primary role is to facilitate connection between people at Mount St. Helens. And many people in Portland don't recreate much at Mount St. Helens or know even much about Mount St. Helens besides the fact that the eruption happened. So it's really a stellar place to learn about volcanoes and what's possible, because the processes that you can see in the landscape of Mount St. Helens are reflected in other volcanoes here in the range, such as Mount Hood.
Well, thank you so much for your time this evening. I learned a lot. I hope everybody else did too. I've got a few closing remarks and announcements for OMSI before we take off. So everybody who joined us, I appreciate you joining us. I hope you enjoyed tonight's event. If you would like to watch the video again or share it with your friends, you can check out the video section on OMSI's Facebook and YouTube pages. And don't forget to follow us on social media for updates on future events and inspiring content from OMSI. And I know I mentioned it at the beginning, but consider supporting Science Pub by making a donation via the Facebook donate button, or you can visit omsi.edu/donate. And join us for our next virtual Science Pub coming up on May 11th. It's a lecture by Dr. Poldrak from Stanford University. His newest book and research is about habits, how they are built in the brain, why they are so hard to break, and strategies to change unwanted behaviors. We hope that you will join us. And once again, thanks to our partner SolarStream for helping make tonight's event possible. As always, you can get more information on our website at omsi.edu. Thanks and have a great night.